Another project we're actively working on is designing electrolyte materials for batteries. Today, lithium-ion batteries are the dominant high-energy density energy storage technology. However, higher energy densities could be achieved by replacing some of the materials in them, and also the electrolyte material that helps shuttle lithium from the anode to the cathode today is typically a flammable liquid, which results in large risks. There is big appetite to replace this liquid with a solid that won't leak out if the pouch is perforated. We're utilizing high throughput simulations, machine learning on literature data, and robotic experimentation in collaboration with others at MIT to design new polymer or liquid electrolytes that address these challenges. Another advantage of solid electrolytes is that they are themselves mechanically stable and allowed to utilize their own stability and physical stability to construct simpler cells. Furthermore, more efficient electrolytes would allow exploring other battery chemistries, such as sodium, which is more abundant and cheaper than lithium, or even so-called dications, such as magnesium, which is again very abundant but hard to utilize in batteries. So discovering new electrolytes could power completely new battery technologies. Today, two large challenges to current lithium-ion battery technologies are cost and energy density. Lithium-ion batteries are still challenging to utilize as grid-scale storage. Renewable sources produce energy intermittently, and ideally we would like to store that energy for when it's needed. However, lithium-ion batteries are proven hard to scale cost-wise and technology-wise to grid scale. So on the one hand, cheaper electrolytes or better electrolytes could allow cheaper chemistries, perhaps sodium or possibly even magnesium, and make grid scale storage more accessible. So on the one hand, there is the chances of enabling new chemistries that are just a lot less costly for grid scale. In this case, maximizing the amount of charge carriers is also critical. For example, lithium-air batteries, this is batteries that utilize lithium as the anode, would be very interesting for aviation because they can achieve very high charge densities. They can be very compact. However, they struggle because, among other reasons, electrolytes are not stable enough. So the electrolytes in contact with the lithium metal surface degrade. So finding a new electrolyte would enable potentially lithium-air batteries, which would themselves be dense enough for aviation applications. Energy density is defined as the amount of charge or total energy that a battery can store by either unit mass or volume mass. And depending by the application, volume or mass may be more important. But in general, the amount of capacity a battery has is related to this energy density. In this project, we have demonstrated machine learning innovations to deal with chemical data and formulation data at the same time, such that we can optimize the formulation of additives that make an electrolyte, as well as the individual chemistries of the battery components. In addition, we have utilized simulations to drive discovery in a quicker way than experimental trial and error. And in collaboration with experimental partners here at MIT, we have demonstrated what's called closing the loop between computer-driven innovation and physical experiments. This platform is demonstrating discovery of new electrolytes, which now must be subject to techno-economic analysis to see whether they can be scaled up and be compatible with current devices.